So today we're going to talk about graphing functions and then using those base functions to translate and transform them into something else. Every function you see on this first page today is going to be what we call a parent function. All right, so y equals x squared, we call that a parent function. And basically what a parent function is, it's kind of like the stripped down version of a car. All right, no air conditioning, AM, FM radio, et cetera, et cetera, et cetera. And from these parent functions, we're going to do things with them. We're going to move them to the left and right, up and down. We're going to stretch them out. We're going to shrink them down, et cetera, et cetera. Now, this whole lesson is a review from last year. You should have covered this already. So I'm going to teach it assuming that you've seen it. I may use a different approach than what your last teacher used. So whatever floats your boat, go ahead and use. Anyways, let's take a look at y equals x squared. Now, under each one of these, I'm going to list the pattern of what happens with y equals x squared. So in general, the parent function, if I take and plug in the following functions for x, I get out the following values for y. And if I was to take and graph that, the parent graph of this, or 2 of 4, looks something like so. So parabola, okay? Y equals x cubed. Again, I've got a pattern of the parent function looking something like, let's go 2, 1, 0, -1, -2, get the y values out, 8, 1, 0, -1, -8. And if I graph all those, here's 1, 1, 0, 0, 2, 1, 2, 3, 4, 8, down 1, over 1, 1, 2, 3, 4, 5, 6, 7, 8. Okay, pretty close. Something like this, something like that. Okay, so those are the parent functions of y equals x squared and y equals x cubed. Moving down, I'm going to take and I'm going to graph the parent function of the absolute value of x. And again, I'm just going to pick some x's and y's. It'll give me some nice clean answers out. And I'll go -2, -1, 0, 1, 2. Get out 2, 1, 0, 1, 2. And this is going to be more linear on both sides. And we've already graphed this, so we know. It shoots straight out this way, straight out this way. Kind of looks like a V. All right, now we're going to move to our harder functions. Y equals root x. Now, it may not be good to pick 0, 1, and 2 for my x values here because I might not get clean answers out. What I want to do is I want to pick the numbers so that I get integer values out when I plug integer values in. So I know I could take a square root of 0. Can't take a square root of a negative number, so I'm not even going to pick that. 1, and then the next perfect square is going to be 4. I can pick 9 if I wanted to. I don't know if I'm going to use that in this case, but I could. Plug it in, get a 0 out, a 1 out, a 2 out, and a 3 out. So if I were to take to graph that parent function, I get 0, 0, 1, 1, 4, 2, and 9, 1, 2, 3, 4, 5, 3. So this graph starts at the origin and moves only right. We can't have negative values. The domain's limited. Our domain in this case, I'll just write that in, is x is greater than or equal to 0. Might be good to know. Now, for the cube root of x, which is another one that you're going to have to know how to graph, be responsible for. This, I want to pick perfect cubes. So What multiplied by itself 3 times gets me an integer out? Well, 8 will do that. I get 2 out. 1, 1, 0, 0, negative 1, negative 1, and negative 8, and negative 2. So here's 1, 1. 8, 2 is right around here. Negative 1, negative 1, 0, 0, and 2, 4, 6, 8 is a negative type, down 2. Looks something like this. Not super great, but close. All right, so these are all of our parent functions, which each and every one of these, we're going to take now and transform them, translate them, move them around. So, a couple of rules. All functions that we've written, and even more, we're going to do logarithms later, exponentials, you name it, can be expressed in the following form. We have some y equals a f of x minus h over b plus k. And each one of these variables has something to do with the movement or the change in the shape of the function. The h value, right here, and notice it's going to be important to follow this exact form, so h follows a negative or a subtraction. The h is going to translate the function horizontally. In other words, it moves all the points to the left and to the right. The k, which always follows a plus, okay, will translate up and down. It means it moves all the values up and down the same amount. Now a, which is in front of the function, and I'll explain that later, acts as a vertical stretch and could be a shrink depending on what we talk about. But I like to call it a y multiplier because it's going to affect the y values of the graph. If the absolute value of a is bigger than 1, the graph is going to narrow because, in a sense, what was a y is now going to be multiplied by a greater number. Thus, a point starting at like 2 is now going to end up somewhere higher than that, or a multiple of that, like 10, and thus that's going to stretch out a graph. If the value of a is in between 0 and 1, then what's going to happen is that graph is going to actually be moved down. So it's going to push it down or shrink it. All right. If I have a negative value, that's going to reflect points over the x-axis. So it'll take something above the x-axis and move it down below the x-axis, as you would expect, because y's go from positive to negative. Also, we have this b value, and notice b is within the function, and it's in the denominator of that expression. And when b is greater than or equal to 0, it stretches the graph horizontally. It makes it become wider. Again, I like to call it an x multiplier because it multiplies an x value from what it was to something bigger than that. When b is less than 1, the graph is going to narrow or squeeze in, if you will. And we know that if b is negative, then all those points are going to reflect over the y-axis. X goes from positive to an x value of negative. All right, so let's do an example, and I'll apply all these rules as we go through. What we're going to start with is this function. Y is equal to the root of x minus 1 plus 3. Parent function in this case is root x. We have a pattern of root x that states if I have 4, 2 comes out, 1, 0 comes out, oops, I'm sorry, 1 comes out, and 0, 0 comes out. Now, I'm going to identify all our pieces to this. A in this case is the multiplier in front of the function, so A is equal to 1. B in this case is within the function, and it's in the denominator. I don't see anything there. It can't be 0, so it's got to be 1. Now, we said that h follows a subtraction sign. Well, following the subtraction sign is a 1, so h must equal 1. And k follows an addition sign, so k in this case is 3. Now, if we go back and think about what our parent looked like, it looks something like this, where our origin was at 0, 0. Now, translations mean every point on that graph is going to move. Well, I'm going to move the origin. I'm going to move it 1 to the right and 3 up. So if I go 1 to the right and 1, 2, 3 up, this is my new origin, the point 1, 3. And now what I'm going to do is I'm going to take and graph this square root function using the point 1, 3 as what you might call a new origin. And I know that nothing's been multiplied to my x or y values. It's just strictly moved over and up. So I'm going to use this pattern to graph my function. I'm going to say, well, this is just a non-affected root function. So I go over 1 and up 1, and I go over 4 and up 2. And then I connect the dots, and there you have it. So that is going to be my new graph of this square root function. Now, what I like to do is I like to just check one point by hand. Notice, I haven't plugged any x and y values into this original function. I've done it all based on a pattern. So I'm going to look at an actual value. Here's 2 and 1, 2, 3, 4. So I have a point 2, 4 on that graph. And I'm going to check to see if that works. If I plug in 2 and get out 4, I'm gold. So I have the square root of 2 minus 1 plus 3 after I plug in that 2 value. So notice I get the square root of 1 plus 3, which is 1 plus 3, or 4. So notice that point 2, 4 checked out. I must have graphed it right. Let's move on to our next graph. Parent function in this case is x squared. And we know x squareds have patterns that look very similar to 0, 0, 1, 1, 2, 4, negative 1, 1, negative 2, positive 4. I notice that my a value again is 1. My b value again is 1, which means there's no multipliers to either my x or y values, where the left side is my x and the right side is my y. I now notice that this is not in the proper form. The proper form says I need to have f of x minus h. Well, what would follow a minus in order for me to get a positive 1, a negative 1? And then I must follow an addition sign. So I have my 4 as is. So in this case, my h value is equal to negative 1, and my k value is equal to 4. So I'm going to move back 1 and up 4 and put a dot here. This is going to act once again like my new origin. So I'm going to set up a fictional set of axes at that point. And from that point, I am going to graph this pattern for the x squared, because I know nothing's been multiplied to this. It's going to look the exact same, with the exception of everything's going to be slid back 1 and up 4. So I go over 1 and up 1, back 1 and up 1, over 2 and up 4, over 2 and up 4. and then I graph my function. Now notice again, I'm going to pick a point to check. This looks like an easy one. This point right here is 0 and 1, 2, 3, 4, 5. So I'm going to plug 0 into my original function and hope I get a 5 out. If I have 0 plus 1, and I square it, and add 4 to it, that gives me 1 plus 4, or 5. So 0, 5 checked. I'm sure that's my correct graph. So now we have a cubic function, and we know that our parent function is going to be y equals x cubed. We take a look at our equation, and it's not in the standard form that we should have. I should have x minus h, so that means in order to have a positive 4, I must have minus a minus. We're cubing that, and in theory, I must follow an addition sign. So to have a negative 1, I must add a negative 1. This determines my a, b, h, and k. Since I notice there's no multiplications, my a must be 1, my b must be 1. We already said our h is negative 4, and our k is negative 1. I'm going to back up 4 now. 1, 2, 3, 4. Go down 1. Put a dot. I need a pattern. X cubes have patterns of 2 and 8, 1 and 1, 0 and 0, negative 1 and negative 1, and negative 2 and negative 8. So from that blue dot, I'm going to draw this fictional axes. And from that point, I'm going to graph this pattern. Go over 1, up 1, over 2, up 2, 4, 6, 8, over 1, down 1, and back 2, and down 2, 6, and 8. Connect the dots. And there's our new x cubed function. Again, I like checking points. This guy looks like an easy one. That looks to be negative 3 and 0. So I'm going to plug negative 3 and 0 into my original equation, and hopefully it checks out. I get negative 3 plus 4. I'm going to cube that, subtract 1 from it, and hopefully I get 0. So this is 1 cubed, which is 1, minus 1 is 0. Checks. I've probably done this right. Let's keep moving. Now we have a situation where we have a multiplication, and it appears to be in our standard form. Y equals x squared is my parent. Y equals x squared has a pattern of x's and y's being, let's go 2, 4, 1, 1, 0, 0, and negative 1, 1, and negative 2, 4. Identifying our A, B, H, and K. Again, I have A's, B, H, K. A in this case is now the number in front of the function, or negative 3. B, there's no fraction within the function, so that's going to be 1 again. H is a 2, and since there is no addition at the end of this, I'm going to give the K value 0. So I'm going to move 2 to the right, put a dot, and call that my new fictional set of axes. Now, this A value, once again, if you went back to the original part of the lecture, we said this was a Y multiplier. In other words, all my Y values on the right-hand side of that T-chart are going to be multiplied by a negative 3. So when I multiply all these by -3, I get -12 for this, -3 for this, I get 0, I get -3, and I get -12. All right. So again, I will make my fictional set of axes. And from this point, I'm going to graph X and my new Y pattern, which reflects a multiple of 3 to all my Y values. So I go over 1 and now down 1, 2, 3. Back 1, down 3. Over 2, down 3, 6, 9, 12. And back 2 and down 12. So notice this graph is much more stretched out vertically than our previous graphs. It drops much quicker. Doesn't open up as wide. I'm going to pick a sample point. Let's go 3 over and 3 down. And check my original function to see if I get 3 and -3. I have plugging into my original -3 times 3 minus 2 squared. That ends up being -3 times 1 or -3. So again, I've checked out and this should be okay. Let's keep moving. Here we go again. X cubed is my parent. I have a pattern of an x cubed function, which goes to 2, 8, 1, 1, 0, 0, 1 of the negative type, -1, -2, -8. And these are x and y values. I take and identify A, B, H, and K. The only thing I would change here is I really want to make it accurate. Say this is plus or -1. I've been doing it all along, so we're good. Turns out that A in this case is a half. B is equal to 1. H is equal to 2. K is equal to -1. So I go over 2, down 1. There's my graph. A is a half, which means that multiplies all my y values by a half. So I'll multiply all those by a half. 8 times a half is 4. 1 times a half is a half. 0, -1/2, and -4. And I'm going to graph these new values of x and y from my new fictional set of axes, which I will make this time in green. So here's this fictional set. From here, I'm going to go over 2 and up 4. Going to go over 1 and up a half. Back 1 and down a half. Back 2 and down 1, 2, 4. And here is my new cubic. And you'll notice that this has kind of been squished down a little bit. It doesn't rise as steeply. Again, I think I'll pick a point. So I'll pick the one that was 2 over and 1, 2, 3, 4 up. This point right here happens to be 1, 2, 3, 4, and 1, 3, 1, 2, 3, 4, and 1, 2, 3, 4. Looks like 4, 3. And I'm going to check to make sure that's correct. All right. Plug into the original function. I've got a half. My x value is a 4. Subtract 2 from that, cube it, and subtract 1, and hopefully I get 3 when I'm done. So that's a half. times 2 cubed. 2 cubed is 8 minus 1. Half times 8 is 4 minus 1, which is 3, and I've checked it out. So it worked great. Let's keep moving. All right, now here's our first appearance of a b value. We have a parent function of root x. We know that a root x has a pattern 4, 2, 1, 0, 0, whoops, 1, 1, 0, 0. We know in this case, I've got to rewrite it so that I'm in standard form. X minus a negative 4. Get the plus 2 on the outside. And notice within the function, so within the root, that's what I'm talking about, within the function, I have a denominator of 3. That's my b value. Out in front, no value, which means a must equal 1. So there's no vertical change to this. But there is a horizontal multiplier of 3. My h value is negative 4, and my k value is positive 2. I'm going to go ahead now and multiply all my x values, because that's what b is. It's an x multiplier, by 3, giving me 12, 3, and 0. So my translated origin now goes back 4, 1, 2, 3, 4, and up 2. This is the point where I'm going to draw my fictional axes. And this is where I'm going to start graphing this new pattern from, where the values on the left are my new x's, and the values on the right are my y's. So this says, start from this point, go over 3, and up 1. Then from this point, go over a total of 12, 7, 8, and go up 2, and draw your new graph. Notice this was a square root graph, and it rises much slower than the original square root, and has stretched out horizontally. I'm going to check once again a point. This point right here appears to be negative 1 and 3, and I'll plug that into my original function. So negative 1 plus 4 over 3, all rooted, plus 2, better equal 3. This is 3 over 3, which is 1, plus 2, which is 3. Checks out, so I should be okay. All right, we're getting close to done. I know it's been a little long, but we're almost there. Now, this is where it gets tough. We notice we've got an x squared function, and we have a pattern for an x squared function normally of x and y being 0, 1, and 2, 0, 1, and 4 coming out. But this is not in the right form. In fact, all of our forms have to be x minus h. This has a 2 in front of it, so I'm going to factor that out. And then I'm going to subtract, or I'll say plus negative 7. Now, you'll notice also that the general form has a division of b. Well, this is a multiplication of b. So how do I say multiply 2 but divide? Well, I divide by the reciprocal. So if I go x minus 5 divided by a half, square that and add negative 7, dividing by a half is the same as multiplying by 2. So now I have it in the form I needed it. A in this case is the value multiplied to the front of the function. Nothing is multiplied there that we can see, so it must be 1. B is the divided term, which is a half. H follows the inside negative, which is 5, and k follows the plus sign, which is a -7. All right. That b value of a half tells us I need to multiply all my x values by a half. 0 times a half is 0, 1 times a half is a half, and 2 times a half is 1. So I'm going to find my translated origin, which is 5 over, 7 down, put a dot there, make that my new fictional axis, if you will. And I'm going to use this pattern of x and y to graph from this point. So I'm going to go over a half and up 1. And then I'm going to go over 1 and up a total of 4. Whoops. So you'll notice that this is squeezed in horizontally. This is the point. What is the point? It looks like 1, 2, 3, 5, 6, and 1, 2, 3, 6, -3. So I'm going to plug that in and hopefully check out. So I have 2 times 6 minus 10, it's all in parentheses, squared minus 7. 12 minus 10 is 2 squared, or 4, minus 7 is -3. Checks. It must be the graph. It was a long one today, sorry about that. Here are your questions. Take a look at the first 3, answer those, then I'll scroll this down so you can get the 4th, and answer that on the form, and we will talk about it tomorrow. Take care.